This lesson will serve as an overview of VXLAN bridging. VXLAN can be broken up into a couple types and a couple use cases. There exists the concept of both VXLAN bridging and VXLAN routing. This lesson is focused on VXLAN bridging. Be sure to check Arista's Configuration Guide, TOIs, Transfer of Information documents, and the EOS Central website for the latest developments. The RFC that first addressed VXLAN was RFC 7348. The draft of that document began in 2011, with the RFC finalized in 2014. You'll find several vendors, including Arista, were part of the development of the VXLAN solution. As with most solutions or features, there is a driving CapEx or OpEx need to solve a particular problem. In this case, one of the original problems to be addressed was the limit to the number of VLANs an infrastructure could support, that limit being just slightly more than 4,000 VLANs. Hosting providers and service providers were struggling to deal with this limit as their data centers were growing very quickly. You can see how they would hit that limit if they were allocating a VLAN per customer. Another issue to be addressed was the sprawl of Layer 2 networking. Anyone that has suffered from a spanning tree related outage knows that those scenarios are very ugly and usually cause a significant outage that can last minutes to hours and in some very public cases, even to days of service disruption. So it became the goal of many network engineers to limit the use of spanning tree in their deployments, favoring Layer 3 designs over Layer 2 designs. But having moved to a Layer 3 design, they would run into problems where a VLAN was bound by Layer 3 either within a rack, a pod, or even a data center. Yet requirements to extend Layer 2 or a VLAN out of a rack, pod, or data center started to flourish, primarily thanks to server virtualization. The challenge grew even stronger when folks started asking for Layer 2 between their data centers for the purpose of supporting vMotion from one data center to another. It was a fair request to make of the network team. It is understandable that the system admins and application owners would like to move workloads from data center 1 to data center 2 without having to reassign IP addressing. So VXLAN can be leveraged to solve more than one problem. Some folks use VXLAN for intra data center extension of layer 2 or the VLANs from rack to rack or pod to pod, while other folks use VXLAN for inter-data center extension as a data center interconnect from data center 1 to data center 2. Arista provides both VXLAN bridging and VXLAN routing to help address these needs. In this lesson, we'll play with some VXLAN bridging, and we'll use a lab to help explain the concept. Here's a drawing that shows an example of how VXLAN could be used as a data center interconnect. In the drawing, we have two data centers, west and east. Each data center has its own leaf and spine layout, as well as a DMZ type pod. In this example, we have a pair of leaves dedicated as the VXLAN VTEPs, or VXLAN virtual tunnel endpoints. Some folks like to call or label these the services leaves. In this example topology, I've connected the service leaves, or VTEPs, to the spines. This connectivity is via Layer 2 MWAG, or multi-chassis link aggregation. We extend the Layer 2 of each data center up into their local VTEPs, and then the VTEPs are connected via Layer 3 WAN circuits. There's nothing particularly special about the Layer 3 WAN circuits, except that they must have jumbo frames enabled. The definition of jumbo frames can vary, and the exact values set to the jumbo frame size can vary as well. At its most fundamental, what we are saying is that we have an MTU that is set larger than the default of 1500 bytes. Since VXLAN is an encapsulation via UDP, we need to make room for the approximate 50 bytes of additional overhead that VXLAN is going to add to our packets. It is this additional overhead that leads to the jumbo frame requirement. That encapsulation is where the VTEPs are adding in our UDP wrapper that provides the VNI, or Virtual Network Identifier. It is the 24 bits that make up the VNI that gives us the ability to mask our VLAN limits and scales the layout to over 16 million unique identifiers. So, in a real world deployment, make sure that you order or ask your service provider to enable jumbo frames all the way through the path from the west data center to the east data center. Be sure to inquire that jumbo frames are not only enabled on the primary path, but also any alternate paths your packets may take during outages or maintenance windows undertaken by your service provider. As you follow the diagram from the left to the right, or from the west data center to the east data center, you can see that we also have our service leaf VTEPs over here, which in turn are layer 2 connected to the spines in the east data center. Note that the WAN circuits do not have to connect directly into our VTEPs. There can be another device or devices to provide the circuit termination. Just be sure that all devices in the path between the VTEPs have jumbo frames enabled. Now, let's talk multicast versus unicast. If you read through the RFC and some of the early designs and deployments of VXLAN, you'll notice that the original transport method leveraged multicast. The reason for this is that we must account for what is known as BUM traffic, that is, broadcast, unknown unicast, and multicast traffic. Setting aside VXLAN for a moment, let's think about how normal switching behaves. When a switch receives a frame, one of the actions it takes is to look at the source MAC address and the destination MAC address. If the source MAC address is unknown, the switch adds the source MAC address to its MAC address table. Next, looking at the destination MAC address, the switch takes a look at the MAC address table to see if there is a match. If there is, fine, the frame is forwarded out that interface. But if we don't have a matching destination MAC address in our table, then the switch forwards the frame out of every interface except the interface that the frame arrived on. This is basic flooding, and it is how we handle broadcast and unknown unicast traffic. When we add in VXLAN, we need to account for this behavior. The original method proposed was to leverage multicast. Each VXLAN VTEP would subscribe to a multicast group. Then, when a VTEP needed to flood the frame, it could do so by flooding or sending to that specific multicast group. Then all VTEPs subscribed to that group would receive the frame. As more and more folks began deploying VXLAN as a data center interconnect, we came to find that the multicast requirement might be a hindrance. Either folks needed to place an order with their service provider to enable multicast, which may or may not equate to a one-time or ongoing additional cost, or if you own the transport, then you may need to enable multicast where you hadn't before. This could be a problem if the equipment or skill sets of the team couldn't support multicast. So several vendors, including Arista, moved to provide a unicast-based method of accommodating this flooding requirement. Specific to Arista, the unicast method is now the standard way to provide the flooding mechanism. In Arista's implementation, the feature is known as Unicast Head-End Replication, or HER. Head-End Replication is achieved by creating a flood list. This flood list provides the unicast IP addresses of the VTEPs that need to receive the flooded frames. There are various ways to configure the flood list. You can configure a simple list that includes all VLANs going to all VTEPs when the replication is needed. Another method is to be more specific with your flood list in that you create a flood list tying specific VLANs to specific VTEPs rather than flooding them all everywhere. And still another method is leveraging Arista's CVX, or Cloud Vision Exchange, to dynamically build the flood list in reaction to the information it gathers from the switches and other integrated services such as VMware's NSX or OpenStack. Regardless of which method is the right fit for a particular situation, the point is that we need to provide a way to mimic the flooding behavior needed to accommodate the BUM, broadcast, unknown unicast, and multicast traffic that we have within the data center and carried across the data center interconnect. We'll leverage hands-on configuration in another lesson to drive home these points and add in a little more terminology.